Tonga, New Zealand sit on an ancient volcanic superplume scientists just discovered. This is the area east of Australia on the Pacific Ring of Fire, and Tonga erupted January 15. It's still erupting, and the ripples of this shockwave have been heard all the way to Alaska and the UK, and the ripples of the gravitational shockwave have been felt up to 40 kilometers distance above our Earth into the ionosphere. So this is the actual area of it, as you can see, and sat images of the ash cloud as well. This has now spread over the north of Australia. It's headed into East Africa. It has crossed the Indian Ocean. This is the exact plume that we're talking about. That's the area of Tonga, New Zealand. New Zealand, we know, has one of the supervolcanoes of the Earth in the North Island, the Taupo volcano, which erupted about 26,500 years ago. And we have super eruptions every 17,000 years, so we're overdue about 10,000 years for a super eruption. Now, this was the Tonga submarine volcano. Unfortunately, of course, the geologists cannot find out what's happening below the surface of the ocean. Only whatever they can track from what they now say the discoloration of the water. Okay, this is the Tonga volcano eruption right there. So, Simon Lamb and Timothy Stern from The Conversation, and this is last year's article, so basically timely. Back in the 1970s, scientists came up with a revolutionary idea about how Earth's deep interior works. They proposed it is slowly churning like a lava lamp, with buoyant blobs rising as plumes of hot mantle rock from near Earth's core, where rocks are so hot they move like a fluid. According to this theory, these plumes, as they approach the surface, they begin to melt, triggering massive volcanic eruptions. But evidence for the existence of such plumes proves elusive, and geologists had all but rejected the idea. Yet in the paper published last May 27, they can provide the evidence. The results show that New Zealand sits atop the remains of such an ancient giant volcanic plume, and we show how this process caused volcanic activity and plays a key role in the working of the planet. And of course, we have the map of it, the Tonga subduction zone. This is the Tonga subduction zone. The Hikurangi Plateau from New Zealand, Tonga subduction zone, the Ontong Java Plateau, and Manihiki Plateau. And of course, we have the Tonga submarine volcano erupting. The two islands that were between the caldera have now basically vanished. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. Unusual vibrations. About 120 million years ago, during the time of the dinosaurs and the Cretaceous period, vast volcanic eruptions under the ocean created an underwater plateau about the size of India. Over time, it was broken up by the movements of tectonic plates. One fragment now lies beneath New Zealand and forms the Hikurangi Plateau. And as the map shows, Southwest Pacific and New Zealand and the Tonga subduction zone shows diverse, dispersed fragments of a once giant oceanic plateau. The red arrows showing the direction of seafloor spreading. Straight black lines show the areas measured in the study. We have had various large earthquakes in the area of Indonesia, Malaysia, the Pacific Orotanga Java Plateau, the Ontonga Java Plateau, and of course the area here has had earthquakes ongoing. And the Tonga volcano, the underwater volcano, is still erupting. This is the day before, ash cloud stretching along the Indian Ocean over Madagascar, now over basically entering East Africa. Now, they measured the speed of seismic pressure waves. effectively sound waves and how they travel through mantle rocks beneath the Hikurangi Plateau. The vibrations were triggered either by earthquakes or deliberate explosions and reached speeds of 9 kilometers per second. It's well known these waves, known as P waves, travel in the uppermost mantle of the Earth at a remarkably constant speed, around 1.8 kilometers per second. That's about 30,000 kilometers an hour. Even small deviations from this constant speed reveal important information about the state of the mantle rock. Since the late 1970s, fast P wave speeds, that's 8.7 to 9 kilometers per second, had been reported from the depth of about 30 kilometers under New Zealand's eastern North Island. That's where the Taupo supervolcano lies. The seismic vibrations recorded in these early data were only traveling in one direction through a small part of the mantle, and the significance of the high speed was not clear. Our new data is much more extensive, they said, from a major seismic experiment in 2012 that spanned the southern North Island of New Zealand and offshore regions, including the Hikurangi Plateau. It showed the speed of P waves reached 9 kilometers per second, regardless of the horizontal direction in which they traveled. But a careful analysis of vibrations triggered by deep earthquakes showed unusual low speeds for vibrations traveling in the vertical direction. Now, as I'm telling you this, I remember what happened a few months back in this exact area where we had very deep earthquakes. Very deep earthquakes. This is before the Tonga submarine volcano eruption. And we were wondering why such deep earthquakes. Well, maybe that is another, I don't know, I'm not a geologist, but maybe that is another prediction of what could be happening underneath these submarine volcanoes. Now, going back to the article, the speed of P waves reached 9 kilometers per second, regardless of horizontal direction which they were traveling, but a careful analysis of vibration triggered by deep earthquakes showed unusual low speeds for vibrations traveling in the vertical direction. This reveals crucial information about how the mantle rocks have been stretched or squeezed by the huge forces inside the Earth, and this turns out to confirm the existence of the elusive mantle plumes. A seismic pancake. The pattern of seismic speeds we observe requires the mantle rocks beneath the Hikurangi Plateau to have been stretched and squeezed in much the same way as one might produce a pancake shape by flattening a rubber ball. And we have computer simulations of the plume of buoyant hot rocks in the Earth's mantle rising up towards the surface from the core mantle boundary, and in later stages the plume head collapses under gravity to form a pancake shape. Now, when we carried out computer simulations, they said, of rising plumes in the mantle, we found they reproduce exactly this pancake flattened pattern as the mushroom-shaped head of the plume spreads sideways and collapses near the surface. We also looked at data from seismic experiments by international teams on other oceanic plateaux in the South Pacific West region. Remarkably, both the Manihiki and Tonga-Java plateaus showed the same pattern as we observed beneath the Hikurangi Plateau. So this area is exactly the same. New Zealand, the Tonga, and Indonesia. Okay, the Tonga subduction zone. It's exactly the same type of flattening. P waves traveled at the same high speeds regardless of the horizontal direction, but at significantly lower speeds in the vertical direction. Reconstructing the ancient SUPER-PLUME, the major oceanic plateau of the Southwest Pacific are now dispersed, but we know how they once fitted together about 120 million years ago. They formed a region underlain by a thick layer of volcanic rock thousands of kilometers across. Our analysis showed this entire region lay above a single head of a giant plume, a superplume, which melted to produce massive lava outbursts over a geologically brief period of a few million years. So this superplume was one, again, underneath New Zealand, Tonga, and Hikurangi, Malaysia, Indonesia, one superplume 120 million years ago. Siberia is the only other place on Earth where this pattern of P-wave speeds has been observed in the upper mantle. It turns out this was also the scene of widespread volcanic eruptions about 250 million years ago. That's when the Great Dying took place, thought to be the cause of the rise of a superplume. This volcanic activity may have changed Earth's climate and triggered a mass extinction that affected the evolution of life. New Zealand and some scattered islands in the southwest Pacific are perched on the remains of what was once an immensely powerful geological force. We don't know whether this process is still ongoing today, but our new seismic technique for finding these superplumes remnants may help us discover more, providing further insight into the many connections between the deep interior of our planet and what happens at the surface. This was from the conversation. Simon Lamb, Associate Professor in Geophysics, Te Herenga Waka, Victoria University of Wellington, and Timothy Stern, Professor of Geophysics, Te Herenga Waka, Victoria University of Wellington, on Science Alert. So there you have it, the connection between New Zealand and the supervolcano, the Tonga subduction zone, the Tonga submarine volcano eruption, and the Ontonga lava plateau of Indonesia. And we still have the, obviously, the latest on the Tonga submarine volcano eruption. We've just had another earthquake. No, yeah, the quakes are still ongoing. Now we have the latest. We have, as we said, the sulfur dioxide plume reaching Madagascar and East Africa yesterday. And the eruption is still major erupting, 5 out of 5 level. So this, I'll do another video. We'll try and find from null school what the gas particles and the chemical composition of the, and also, of course, very important is the wind direction, how the wind is bringing this ash and where would we believe that it could be heading. So please leave your comments and thank you for your support.